Hi, and welcome to today's webinar, How to Document Safety Instrumented System Inspections and Tests. My name is Katie Turner. I'm the Beamex Marketing Manager here in the United States. I will be one of your hosts for today. I'm joined by Lindsay Fair, a Beamex Client Services Manager, and Michaela Cooper, ISA Coordinator with ISA, and they will help me host the webinar as well. Before I hand it over to Lindsay to introduce today's speakers, I'd like to let you know how you can participate in today's webinar. Before we begin, I want you to know that this will be more like a conversation. We'd like you to interact with us, and as you can probably already see, we will be using video, so you'll be able to see the presenters' faces today. There will be two question and answer sessions, one about 10 will be about 10 minutes and the other will be at the very end. Because of the large audience today, we will only accept typed questions, so please type those into the question and answer box. There will be live polls during today's webinar, so we do encourage you to interact with those, and you will see them appear on your screen and you can actually answer the questions. We'd also like to know what you want to see next. So please answer the survey that will appear in your browser at the very end of the webinar. So before I hand it over to Lindsay to introduce the speakers, I'd also like to let you know about the Beamex Calibration YouTube channel. It's by Beamex, and it's also includes videos of how to perform calibrations as well as more information about our solutions. So with that, I'd like to hand it over to Lindsay to introduce today's speakers.
Thank you, Katie, and good afternoon to everyone. Our first guest speaker is Paul Grun, who is a global functional safety consultant with AE Solutions in Houston, Texas. Paul has specialized in safety systems for over 30 years. He is an ISA Life Fellow, co-chair of ISA 84 Standards Committee, the developer and instructor for ISA courses on the subject, and the primary author of ISA book on safety instrumented systems, design, analysis, and justification. Paul developed the first commercial control and safety system modeling software over 25 years ago. He has received his BS in mechanical engineering from IIT in Chicago. Paul is the professional engineer licensed in Texas, a certified functional safety expert, a member of the Control System Engineering PE exam team, and the ISA 84 expert. Paul is the 2018 ISA President-elect and Secretary. Our next guest speaker is our very own Ned Espy, who's the Technical Director and has promoted calibration management with Beamex for over 20 years. Ned has helped develop best practices for calibration with a focus on pressure, temperature, and multivariable instruments. He's a consistent editorial contributor to leading industry publications and has received significant recognition within the automation industry. Today, Ned teaches calibration best practices and provides technical support to end users and the Beamex team in the United States. And last but certainly not least, we have our very own Roy Tomolino, who has been teaching calibration management for over 50 years.
Okay, Paul has a picture. He looks like James Bond, and I get a pirate picture? What? All right, I'm out.
You know what? I love it. Throughout his career, he has taught on 4 different continents to people from over 40 countries. His previous roles include technical marketing engineer and worldwide trainer for Hewlett-Packard, as well as application engineer with Honeywell. Roy is a calibration evangelist and conducts training sessions and gives technical support to Beamex customers. I want to thank you all for your patience, and I'm going to go ahead and pass this over to Paul so he can start this webinar.
Thank you, Lindsay. So 2 slides covering the agenda that we'll have today. We'll go over what is a safety instrumented system and why maintenance and inspection and documentation is important. We'll have a Q&A session after that portion, which will be about 20 minutes as far as presentation. Then we'll pass it over to the Beamex folks who will go over some real examples of documentation and test procedures. We'll have a demonstration of a paperless system and our final Q&A session. And a wrap up. The portion I'll be covering is what is a safety instrumented system and a safety instrumented function. The standard talks about the 2 failure modes of systems. Those are safe and dangerous failures, and that's important because that will give the introduction of why safety functions need to be tested and documented. And the standards now go over the importance of thorough manual testing, that in your calculations of system performance, you need to include the impact not only of diagnostics, but of imperfect manual testing. And I'll go over the math, simple math that's behind all that, and to show the importance of thoroughness of testing, how you can optimize what your test intervals need to be so you can save money, management of change and tools that are available to help assist and document management of change, as well as the importance of having a centralized database and the benefits that provides, rather than diverse manual forms and spreadsheets and various other documents that make things very, very difficult to track and utilize and get the real benefits from all that. And all of the testing and inspections need to be documented in some manner, because the basic statement of if you didn't document it, it didn't happen. So an auditor or an assessor will have nothing to prove that you've actually done what the standards and regulations say you need to be doing. So we'll have a poll question now. Is your facility covered by the OSHA, Occupational Safety and Health Administration, Process Safety Management, the PSM regulation? That's 29 Code of Federal Regulations 1910.119. So please take a moment to answer this, yes or no. That regulation, for a little bit of background, came out in 1992 because of a number of major accidents that we had here in the US. So that regulation has 14 various clauses. It's a fairly short read, but quite all-encompassing, and actually going through some changes, or has changed in some states like California. They've added to it because we've obviously learned a lot more about process safety over the last 20 plus years. And the results of that poll are, as I would have hoped, the majority are, maybe those who aren't, are engineering firms or vendors or others who they themselves are not directly covered by the regulation, but they are probably supporting others who are. That regulation says you have to follow various industry standards, REGAGAP, recognized and generally accepted good engineering practices. OSHA has written 2 interpretation letters stating that the ISA 84 standard on safety instrumented systems is recognized and generally accepted good engineering practice, and organizations have been fined, some significantly, for not following that standard. So that standard talks about a safety instrumented system. There have been many names for these systems in the past. A common one used to be ESD, which we took as emergency shutdown system, but to an electrical engineer, ESD is electrostatic discharge. So you need to be very careful when you're using acronyms because you'll confuse people. And this topic has no shortage of acronyms. You can see a couple on the slide right here. So the basic process control system, which it could be pneumatics, it could be single loop controllers, it could be PLCs, a DCS, hopefully those acronyms are well known. That is what is controlling the process. You have your sensors, your logic, your final elements, and controlling temperature, pressure, level, and flow. So a simple question I like to ask people is, how many of you believe that the control system is perfect and will never fail? And that usually results in grins and giggles, and everyone realizes everything fails. It's just a matter of when. So, I mean, if the control system was perfect, there would never be an alarm. You would have no need for relief valves. There would be no need for fire and gas systems because nothing would ever go wrong. That's not reality. So we have a variety of safety layers. And in terms of instrumentation, we have a safety instrumented system, which again could be any technology from pneumatics to electronics to programmable systems. They are typically designed with their own separate sensors. They're definitely their own logic, and their own final elements as well. So the safety system is phrase it differently. The control system is an active, dynamic system. People know when it's working and when it's not. But the safety system is not controlling anything. It's a dormant, passive monitoring system. It's monitoring temperature, pressure level, and flow, and only takes action when those variables go outside their normal range. So how do you know if it's working? The only way is by testing the system. Either it must have very thorough diagnostics on its own, or you must manually test stuff. And this is very important with the field devices. The logic solvers generally have plenty of diagnostics and information they can provide. Transmitters are getting certainly much better in that regard, but no diagnostics are perfect, and final elements are generally the weakest link of all, and everything needs to be tested. So the standards talk about the failure modes of safety systems. And for example, just to intro this, I know people who have had relay-based systems, replaced them with a PLC, implemented a programmable logic controller, implemented the same logic, and had an accident because they didn't understand the impact of the technology change. With safety systems, the issue is not so much how does it operate. The issue is how does it fail, and how can you or the system recognize a failure? So the standard talks about two failure categories. We can argue over the names, but this is what's been in existence for more than 20 years. Safe failures are essentially a nuisance trip. This is where there is no hazard in the process. There is no high pressure or high temperature, but the system fails in a manner that shuts the process down. So for example, your normally energized valve, the solenoid coil just burns out and the valve is going to go closed. That's going to shut things down. There's nothing safe about a nuisance trip. We all understand that. The main concern is lost production downtime and economics. This has nothing to do with SIL, safety integrity levels. Safety integrity levels is only a measure of the performance of dangerous failures, what I like to call I'm stuck, I'm not going to work when you need me. So your transmitter is stuck at 10 milliamps and not responding. Your PLC is stuck in an endless loop and not responding. Your valve hasn't moved in 2 years, and when you de-energize it, it's stuck. It doesn't move. These are all examples of dangerous failures, and this is why systems have to be tested, because there are dormant, passive systems that can have dangerous failures that no one knows about, and because the valve is never moving, or the logic solver is never changing state, or your pressure switch, if it's a dumb device, never changes state, how do you know if it's actually working? This is why systems have to be tested. The testing has to be thorough. The testing has to be documented. And the maintenance records have to be available to be reviewed to make sure all of the assumptions we made in the design at the beginning, for example, failure rates, actually match what's happening in the real world. So PFD, probability of failure on demand, which is we'll see on a way of ranking or deciding what SIL, safety integrity level, your system meets, is only a measure of dangerous failures. You would find dangerous failures during the operation and maintenance phase in the ISA 84 standard, which is the same thing as IEC 61511. IEC is the International Electrotechnical Commission. This is clause 16 in the standard on operation and maintenance. You have to do periodic maintenance to make sure the system is actually functioning as intended and meeting the performance requirement that you determined early on and did your calculations to try and justify. The technicians and people doing this work need training on what the function does, what it's protecting against, how they're going to do bypasses, how they're supposed to do testing. You need to have thorough procedures. So people will follow procedures properly. They just don't make things up on their own. So what do they do and how are they supposed to do it? We'll see some examples with testing procedures. People need to understand why systems need to be tested. Again, I've tried to stress that to detect dangerous failures that would be unnoticed. And you determine what the test interval needs to be based on doing some simple calculations. Even visual inspections to make sure that nothing has been deteriorated, that the insulation on wiring isn't coming off, that connections are tight, that corrosion isn't a problem, that all the bolts on an enclosure are actually there, that a reset lever on a solenoid isn't wired in the reset position, wired to a piece of pipe, so it's always in the reset position. Visual inspections can help. And all of this needs to be recorded. Again, if you didn't document it, it didn't happen, and that can lead to some serious problems. That one questionnaire, don't really have time to get into recurring problems, but see if there's any questions on that. So some devices, for example, a switch, a relay, a solenoid, a isolation valve, these are considered dumb devices that have no diagnostics. They have no way to detect a dangerous, it's stuck, it's not working failure. So you must test for all failures manually. But some devices, anything with a microprocessor essentially, is a smart device and does have a level of diagnostics. Now, the safety PLCs have virtually 100% diagnostics, but no field device does. So there are still tests that you must do manually in order to make sure these devices are functioning properly. So this brings us to our second question of, do you do probability of failure on demand, PFD calculations, within your organization to see if your safety instrumented function is meeting the required safety integrity level that was determined in the design phase of how well does this system need to function? And the results of that one are similar to the earlier poll. 70% are saying yes, 30% no. The standard is fairly clear. If you're following, or if you have a covered facility and you'd be following the 84 standard, it is clear that you must verify the performance of your system based on a calculation. There are hardware fault tolerance tables also that we'll take a peek at. You could say, well, I'm just buying certified stuff from the vendors and they say their device meets SIL 2, so I'll just use all SIL 2 rated devices. That's no guarantee that anything is actually going to meet your SIL 2 performance requirement. You still have to test things and follow the safety manuals and the design and implementation of those devices according to the vendor. So what's the impact of testing and diagnostics? For example, so PFD, probability of failure on demand, if you had a device that you never tested it, eventually the device is going to be failed at some point. Everything fails, it's just a matter of when, and the longer the time, the greater the probability of it failing. But if we manually test something, and every year, for example, let's assume the sawtooth is based on every year I test it, and the device works, and if we've done a thorough test, we can assume that, well, the device is as good as new now, in basic theory, so my probability goes back down to 0, and after a year I test it again. So we get this sawtooth pattern, so the PFD average over that interval can be determined by simple calculations that I'll be showing you shortly. And we can then match that to the required performance table that we'll see in a moment. So not going through all the calculations for all different configurations, but this is the basic formula for calculating probability of failure on demand for a simplex or non-redundant device. The black portion is if a device has diagnostics, so it's the dangerous detected failure rate, and there's a mean time to restore or repair. Terms have changed subtly in the standards. Test intervals, whether they're automatic testing, which is usually almost seconds or scans on an intelligent device, and that black portion has a minor impact. The blue portion has a significant impact, and that's the dangerous undetected failure. Those are the ones that you have to manually test for as thoroughly as possible with whatever your test interval manual is. But since devices and manual testing is not perfect, there is the red portion that the standards now talk about that you need to include what I've at least termed here the dangerous never detected failures that could be in there for the mission time or life of the device. And that can have a significant impact, as we'll see. The bypass duration we're not really going to cover in this depth here. And we can determine what those failure rates are by these basic little calculations, knowing from the vendor typically is the only one who can tell you what their diagnostic coverage is. There are some documents and some vendors now releasing, here's different manual test methods, and depending upon which method you're using, here's your manual test coverage factor. So you can do these calculations, and we'll actually have an example running through this. So let's start with some basic assumptions. Again, the point of this is to show you why systems need to be tested and why thorough testing is important. Let's start with just a transmitter. Let's say the mean time to fail is 80 years. It's not life. That means If you had 80 transmitters in 1 year, after you test them, you find one transmitter that is not responding properly. And let's assume it's a safety certified transmitter that has a very high level of diagnostic coverage. Coverage automatic is the acronym there. And let's assume that's 90%. Now that's optimistically high, but let's at least go with that number here. Let's assume we're doing yearly testing. Let's assume that I isolate the transmitter in the process. I pump up a pressure. I see that it responds at the set point that we've determined. Sounds like a 100% effective test to me. And we're not going to bypass. We're not having that portion in our formula. So here are how we calculate the basic numbers, starting with the dangerous detected. So failure rate and mean time to fail are reciprocals of each other. I go over this in the longer classes to get people used to all these ideas. We have a 90% diagnostic coverage factor, so there is my dangerous detected failure rate. Dangerous undetected failure rate, that's using our formulas that we saw in the earlier slide. We get a much smaller failure rate, a larger mean time to fail. There are no dangerous never detected failures because we're assuming perfect testing. There's the formula. There's how we plug numbers into the formula, keeping all the units the same, assuming a 48-hour repair time. So if I do find something that's wrong, I fix it. The test interval automatic is seconds or scans. So 48 hours plus 2 seconds is 48 hours. So that kind of drops out of that. And you get a number, and adding the probabilities together, we get a PFD of 6.9 e to the minus 4, which no one relates to. Probability numbers are expressed in scientific notation. They go over people's head. Even engineers get the numbers wrong, realizing what integrity level that can fall into. So about 20 years ago, almost, we developed a new term in industry that didn't exist back in 1996 when the first edition of the standard came out. So it's the risk reduction factor, is simply the reciprocal of PFD. So it's much easier to see the difference between 10, 100, 1,000, and 10,000. So we get a risk reduction factor of 1,400, 1,450 if we want to be picky. Now, if we add the rest of the system now, so a sensor is not a safety instrumented function all by itself. We have a logic solver. So we'll take that transmitter, we connect it to, many people are using dual or triple redundant, certified for use in SIL 3 safety PLCs that are basically nothing more than noise in the calculation. And we have a final element. Now let's be actually optimistic here, assuming we have a valve with a dangerous mean time to fail of 50 years. Again, that's not life. Let's assume we have 50 valves. When we test them after a year, we find one, only one out of 50 that is not responding properly. That might even be optimistic according to some data that's out there. Now let's assume some diagnostics with that valve. Let's assume partial stroke testing, which ISA has a standard and technical reports talking about this issue as well. Let's assume weekly automatic partial stroking. There's over a dozen ways this can be done. Lots of vendors have solutions for this. And let's assume a optimistically high 80% diagnostic coverage factor of doing a weekly partial stroke. We're not testing that the valve actually closes. We're just testing that the valve is not stuck open, which is the primary failure mode for a valve that never moves. Now, we'll assume, again, perfect manual testing and no bypassing, that fourth factor in the calculation. And our total number, just using the same basic calculations we had before, we get a risk reduction of 350, because you add the probability of failure on demand of the sensor plus the PFD of the logic plus the PFD of the single valve. Probability increases, so the risk reduction factor goes down for the total system. So what does a risk reduction factor of 350 even mean? Well, the standards talk about safety integrity levels. We have levels 1 through 4. 4 is generally considered not acceptable and you would redesign. Level 3 is not very desirable either. But a risk reduction factor of 350 falls into the middle of the SIL 2 range. So if you did your LOPA, layer protection analysis, or risk graph method, or whatever you came up with and said, we need to meet SIL 2 for this function, I've now done a calculation to show that yes, you meet SIL 2, which was your target. Now this is assuming yearly testing and very thorough testing. So you have to ask yourself, are you actually testing devices this often, and do you think your tests are 100% effective? Now there's also a table in the standard, the fault tolerance requirements for field devices. Now, we've been modeling here and assuming non-redundant systems, which means the fault tolerance is 0. If this device does not work, the safety function won't work. Whereas a fault tolerance of 1 would mean even if a device fails, I have another device that can still do the function, meaning you've got 2 sensors and 2 final elements in what would be termed a 1 out of 2 configuration, which we don't have here. We just have a fault tolerance of 0. So this table is trying to imply, hey, this only meets SIL 1. Yeah, it depends on the assumptions. So there are clauses listed at the bottom of the slide here. Clause 11.4.3 says the fault tolerance numbers may need to be increased by 1 in certain cases, primarily if the devices are not fail-safe. And clause 11.4.4 says these numbers can be lowered by 1 if you meet certain criteria, primarily prior use. Just don't have time to go over all that detail. So it is possible to meet SIL 2 with non-redundant stuff. And clause 11.4.5 says you can use the more detailed tables in the IEC 61508 standard, which are based on safe failure fraction, another concept we don't have time to get into here. But my formulas and the calculations we've been doing meet the requirements and stuff covered in the higher level standard. So just saying, yes, it is possible to design SIL safety integrity level 2 with non-redundant field devices.
Paul, this is Ned. I have a quick comment.
Sure.
Your early slide, you showed the control system and then the safety shutdown system. You know, they're semi-independent. But I noticed you had 2 pressure transmitters on that tank. So by having the second pressure transmitter, does that give you the redundancy that you're talking about with the SIL?
Good question.
Make it like a SIL 2 level?
Good question. The second transmitter on that tank or vessel, one was for the control system, one was for the safety system. They are completely independent. In most SIL selection techniques, for example, layer protection analysis, you would probably take credit for the control system for doing some level of risk reduction, or it might actually be the initiating event that could cause the problem. For example, it's stuck or it's not responding. So I can't take credit for it twice. So no, we cannot count those transmitters as dual redundant. The model that I basically did a moment ago with the numbers assumed for that transmitter would be assuming pretty much a certified for use in SIL 2 transmitter with a 90% diagnostic coverage. Most general transmitters only have in the range of like 30 to 50% diagnostics, and that would not meet the SIL 2 kind of performance requirements.
Okay, thanks.
If you're going to claim 1 out of 2 sensors, it would need to be 2 sensors specifically for the safety system. Now, there's actually, you brought up a good point, and don't want to get too deep into this, but I can even take a standard transmitter that only has maybe 30% diagnostics, but compare that signal with the control system transmitter. We could argue about where we do that comparison. And I can then claim, perhaps in a range of 90% diagnostics of that general transmitter, simply because I'm doing a comparison with another device. So there's a variety of doing comparison diagnostics like that, but I'm still not considering it 1 out of 2.
Gotcha.
So that was assuming 100% perfect manual testing. So in the earlier formulas I showed, that third portion, the red portion, dangerous never detected, was 0, didn't impact. But what if we now claim, instead of our manual test not being 100% effective, but it's only 95%? For example, maybe we're not actually testing the impulse lines on the transmitter. Maybe we can't actually test the transmitter in situ. We have to remove it and take it to the maintenance shop. Maybe we're not actually testing the transmitter with liquid to measure level. We're actually doing it with some other measurement or some other way to make the sensor respond. So it's not a 100% effective manual test. Maybe with the valve, we're not actually testing cycle or stroke time. We're not actually testing that it's sealed and stopped flow. So in reality, our test is not 100% effective. If we just assume it's 95% effective, which is grossly optimistic, how much do you think the answer might change? If we're just changing the factor 5%, do you think the answer would only change 5%? So would our risk reduction of 350 just be reduced by 5%? Or might it be more? The standards say you need to include this in your calculations now. Well, here's how we do it. Again, it's not complicated math. A 14-year-old kid in high school could do this basic math. But graphically, let's see the impact of this. So as we saw before, if I never test, my probability eventually goes to 100%. But if I test yearly and assume perfect testing, I'm back down to 0. But in reality, you're not coming back down to 0. In reality, for example, you don't leak test the valve, or you're not actually testing the liquid level with liquid. For example, at Texas City, one of the problems they had was their level float. They weren't testing it with liquid. They opened a connection on the bottom, stuck a metal rod up inside, pushed the float up. The contacts changed state, and they considered that a test. Well, unknown to them, they'd actually poked a hole in the float over time doing this, and it would never float with liquid. So their test was 100% successful, but it would never respond in reality. So again, your tests need to be thorough. And if you're not doing thorough testing, that portion that you're not testing, the probability of that failure now increases over time until the mission time or the life of the device when you either rebuild it or replace it, and then you assume you come back down to 0. So our PFD number, the second dotted line, is impacted rather dramatically. Now, how would we do the calculation? Well, with the numbers that we had and the assumptions we made, the dangerous detected failure rate is the same. The dangerous undetected failure rate now is impacted by 95%. But we now have this third factor, the dangerous never detected, which the failure rate is tiny. The mean time to fail is huge. So you think, well, how much of an impact could this actually have? Well, you don't know until you do the calculation. And if we assume, for example, a 15-year life or mission time, maybe you rebuild the valve after 15 years, most transmitters won't last beyond 15 or 20 years. So let's say we just replace it. That now has a significant impact on the calculation. So most people, again, don't relate to probability numbers, but what was for the sensor alone, 1450, is now lowered to less than 900. Changing the proof test coverage by 5% impacted our answer by almost 40%. Now, when you add the rest of the system to it, our 350 for the system is now reduced to 190. That's almost a 50% impact here. Now, we're still at the low end of SIL 2, which is anything greater than 100, but this can have a considerable impact. And this is, again, assuming an optimistic, probably 95% proof test coverage. So if you're only doing 80 or 70 or 80% effective testing, and some of the vendors can tell you, with this test method, here's your proof test coverage, you may potentially not be meeting your SIL targets. Now, how often you need to test can be determined by the calculations that I've been showing you here. And even other records, for example, you have an accuracy value you're trying to shoot for with a transmitter. Well, if you do periodic testing and you can show, look, I'm always meeting this accuracy level, I don't really need to test every quarter or every 6 months, maybe I can stretch it out. So having records of this and having electronic databases where you can track all this can provide a lot of benefits. Everything changes in the real world, whether it's transmitters change, set points change, but you need to follow with a safety system. It's extremely important. It's clause 18 in the standard on management of change. Don't change anything unless you know why it was originally done that way, but in the real world that doesn't always happen. I know of an audit that found 30% of the sensors were not configured according to the project documentation. So whether it's someone just replacing a transmitter at 2 in the morning and not really checking how it's supposed to be configured, it's this brand and it's the same brand and model number, they didn't realize all the details. People need training on this level of detail. But if you have software tools and databases that can track this automatically, so rather than having to check it manually, there are tools available now to help track this automatically. So as I mentioned, you need to document all this sort of stuff. And in the past, basically before computers, everyone was documenting all this manually. And many people are still documenting all these test records manually. But that makes it very difficult to check records and see whether my failure rates match what I assumed in the original design. So there are a variety of tools and software programs available now to automatically track all this. There are a number of vendors who offer safety system lifecycle tools that will connect to your SAP system or anything else and your historians and can be sucking this information out. So rather than having to manually try and identify problems, you can automatically have dashboards that will show your failure rates are not what you assume them to be for these particular functions. that these devices don't match the configuration of how they're supposed to be configured according to project documentation, and you're not doing the manual testing at the intervals that you said you were. So again, trying to track all that manually would be virtually impossible. But now, again, it can be automatic, and there's all sorts of benefits. If you actually had a window into the systems like this, you can have a better idea of what level of risk you're actually meeting and whether it matches what you assumed in the original design. So, Katie, handing things over to you.
Yes, thank you, Paul. Okay, we are gearing up for our first question and answer session. But before we do, just to let you know, if you're looking for more information about what Paul was talking about here today, ISA does offer several reference books and training. The first one on the list, Safety Instrumented System Design, focuses more on the calculation that Paul went over, while the second book listed, Safety Instrumented Systems Design Analysis and Justification, includes more about the whole SIS lifecycle. And that is also turned into an ISA training class, as you see here on the PowerPoint. And there is another one that's related called Installing, Calibrating, and Maintaining Electronic Instruments. So again, if you're looking to be further educated on this topic, please check out these additional resources. The second one that we have here available that is actually a free resource and will be coming out very soon is Calibration Essentials. So this is related more to calibrating instruments, but it's going to be 60 pages, 11 articles, all about calibration. So with that, I will turn it over to Lindsay for our first question and answer session.
Thank you, Katie. Okay, now we're moving to our first Q&A session. We've received some really good questions so far, but I'd like to encourage you to join the discussion by submitting your questions. And you can do this by the question and answer box on the right hand of your screen. If we don't get to your answer during this session, we will add it to the final Q&A session. So, and again, we're going to have to limit this to about 10 minutes. So we'll get through as many as we can. Our first question is, why would the oil and gas industry rely on switches rather than transmitters?
Well, this is Paul. I'll take a shot at that. Switches have been used for virtually 100 years, and people were using relay logic for safety systems up until the 1970s. And relays obviously don't understand what to do with a 4 to 20 milliamp signal. So switches are actually still the most common input into devices even today. Switches tend to be less expensive. Many people are trying to save costs as much as they can. But it is true that more and more people are migrating to transmitters for the benefits somewhat that I showed. The transmitters are intelligent devices, have a level of diagnostics, can meet higher integrity levels than switches can. But whether it's the oil and gas or any other industry, switches aren't going away. Roy and Ned, I don't know if you have any.
No, that was a good answer. I mean, as far as our customers, switches are very prevalent and, you know, need to be tested on a regular basis.
All right, thank you, gentlemen. We're going to move on to our next question. And this is the SIS tools mentioned. Are these specific to new systems and applications, or can they be implemented on legacy systems as well?
Yes, they can be implemented on legacy systems.
Yeah, and there's a lot of options out there. I've learned a lot in this, preparing for this webinar, and there's a lot of good information out there on the web that, you know, and obviously consultants, engineering firms that specialize in this can give you a lot of good guidance.
Okay, on to the next question. Testing trip valves during a TAR was 100% acceptable. What is it now?
So testing valves during a turnaround was 100% acceptable. That's typically when people would test the valves, was during a turnaround, which often people abbreviate as TAR. But many people are stretching their turnarounds to 5 and 7 and even trying to go beyond that. And if you leave a valve in a single position for 5 years, I'm pretty confident it's going to be stuck. Some prescriptive standards for boilers and heaters and such pretty much mandated yearly testing. Sometimes people might stretch it to 2 years, and there's documentation showing, look, industry has experience with stroking valve periodically and they'll work. But if you go to long intervals, there's no evidence to show that that's going to be suitable at all. So you're going to need, if you're having a turnaround every 5 or 7 years, you're going to need to build in the capability of doing some kind of online testing. Partial stroking can provide some benefits. Maybe your unit shuts down occasionally for some other reasons between turnarounds, and potentially then you could be doing testing or taking advantage of, well, hey, the unit had a nuisance trip. I saw the valve close. They stopped flow. I can consider that pretty much a valid test. Not 100%, but it just depends on how much documentation and checking you're actually doing. So actually, we've done some of my fellow coworkers have done some papers and presentations on that impact and what can happen if you're really stretching out your test intervals very long.
Yeah, I see the same thing, Paul, and I think what you bring up is that there's a cost when you stretch something out. You can't just take pure savings. There's definitely a cost of maintenance that you need to consider and able to achieve that kind of extension.
To give an analogy that I think everybody could relate to, you drive your car every day. How confident are you that tomorrow morning it's going to start? Very confident. But if you let your car sit in the garage or out at the airport for a year, how confident are you that when you go to it a year later that it's going to work at all? And a valve is even more mechanical than that. So then you ask a solenoid manufacturer what they recommend is their test interval. I guarantee you it's not 3 to 5 years. It's generally on a monthly kind of basis. They won't always tell you that, but if you ask, you'll get some interesting answers.
Would you like to add anything, Roy?
Unmute, Roy.
Thank you.
Yeah, so I will figure this out pretty soon, but my issue isn't with valves, it's more with Paul. So I want to take exception to your example of any 14-year-old in high school can do this math. When I was 14 years old, my math class was this. Johnny has 2 apples. Susie pushes Johnny down and takes one of his apples. How many does he have left? So I'm not really sure that a regular 14-year-old can do that math. Maybe it's just me. But that's all I have, Lindsay.
Okay, this is going to be our final question for this session. How does OSHA 1910 compare to OSHA PSM?
They're one and the same. So a lot of people talk about the PSM regulation. They may not even realize what it is or where it came from. And that's 29 Code of Federal Regulations, CFR 1910.119. That is the PSM regulation, and that came out in 1992.
All right, time is up. I want to thank everybody for participating, but please continue to submit your questions and we will get to them shortly. I'm going to go ahead and pass this over to Ned Espy for his presentation.
Okay, so hope everybody's still with us. Really enjoyed Paul's comments there. I've really learned a lot here today and getting prepared for this. So we're going to change channels a little bit, and we want to ask a question. It sounds like 70% of you out there have SIS going on. So we'd kind of like to analyze, how are you documenting? Are you strictly paper-based, or are you able to use tablets, laptops to collect data when you're performing your proof tests? or is it some combination, or are you doing testing but not, not doing complete documentation? Or if it doesn't fit, tell us some other answer there. Okay, so the vast majority of you are trying to do a combination, but then there's a chunk of you that are strictly maybe paper-based. So yeah, obviously with this kind of documentation requirement, the goal is to maybe get electronic, but it's a difficult path maybe to get there. So thank you for those responses. So I have two examples to go over, and I know these are hard to see on the screen, but these are real tests from customers that I wanted to share. And just looking at this is a multi-page document, and this is sort of a minimalist approach. And one of the things Paul mentioned is design these tests for your personnel. Make sure it fits their level of expertise, and it doesn't have to be down to the micromanagement of information. But looking at this form, it's got on page 1 a little header section, and it is a little fuzzy because this is a copy of a copy. So this form has been copied and utilized over and over the years. So it's something, it's totally paper-based. But on this first page, it would be good if you had maybe an overview or a description of the whole procedure and what the objectives are and things like that. Here's a listing of tools and other requirements to perform the test. And then here's a sign-off sheet with the team of people that perform the test. And I notice here there's some blanks. And really, when you design these tests and forms, blanks should not be acceptable. I mean, you really should try to verify this information and make improvements to how you're doing things. Here's the following pages. Here's some more, maybe here's some overview information. But notice that some of these tasks have as found, as left, and comments, but sure isn't a lot of room for comments here. And then some of these steps don't have any real place for comments. So just pointing out some differences here. And then here's the final page. And look, here's a comment out here in the margin because there really wasn't an allowance for it, and it actually says repair air leaks. And this is great that the technician made a comment along these lines, but maybe this is sort of an as found and as left. So there was an air leak as found, and then they made this repair and as left it would pass. But maybe more information sure would be helpful here. What was it due to corrosion? Was it due to some physical maybe it's exposed some way so that it got damaged? Maybe just requires some simple protection. So it sure would be good to get more information than less or minimal information. So just as a review, looking at this example, it's real important to me that you have some kind of overview so that the team knows, what and why you're doing things. And having blank fields is a red flag to me. So, you should design these tests in steps to where nothing's left blank. And as Paul said earlier, everything needs to be meaningful and thorough. To have a step on there that's just a sort of a rubber stamp thing, beware that you pass on a light attitude to the people collecting the data. And do allow maybe a little more room for comments and educate your people to provide more information. It's really critical one of the things Paul taught me in preparing for this is that we don't care when things pass. That's what we're expecting. But when a failure occurs, that's when we really want to know as much information as possible about what caused something to fail. And then, when a change is made, try to keep this as found as left mentality in mind. And then finally, I didn't say it on this, but this form indicates that there's really no procedure for review. It would be good practice to have a place for final comments, maybe by a reliability engineer or somebody that would review this data and then could perform some analysis to take corrective action for future tests.
Ned, to add a comment?
Yeah.
I'm not sure if you phrased it the way you wanted. It's perfectly acceptable to have devices that fail. Technicians should not think that a device failing somehow reflects badly on them. It is in everyone's best interest, if something fails, that they document it so other people are aware of it. It is perfectly acceptable to have things that fail. We just need to know about it, document it, and track it so we can compare it with the failure rates that we assumed early on.
Excellent point, Paul. Thanks for chiming in on that. We see that in calibration. People don't want to say something failed on a test, and when you can adjust it and make it good as new and back to 100% safe functionality, that's a good thing, and as you say, it's so important to understand what is failing and how how can you prevent that from happening again, or minimize that from occurring again. So excellent point. So here's another example, and I jumped ahead here, but this is a 4-page document. It's actually 30 some steps, and but right off the bat, you'll notice that this is like a template. So probably, this company has this kind of information on every test. And then notice there's warnings that are in a different color that kind of jump out at you. So here's some things that, it's got more detail and a lot more information jammed into the piece of paper. But this has obviously gone through a good verification phase. And I don't have this one filled out. This one is a blank. But let's see, I jumped ahead. I'm sorry. But down here, notice there are some places for the team to sign off. Here's a bigger comment section that's maybe for the entire test. And it does look like there's definitely some procedures going on here post data collection. So just to summarize some of the points I'm trying to make here in showing you these forms is, and I created this list a little bit from Paul, but I found a paper that happened to be authored by some of his peers at AE Solutions. And this was actually presented at the ISA Automation Week back in 2013. So if you want to, I'm sure you can find this if you Google it. You can find it at AE Solutions or at the ISA website. But and you're going to hear some things that Paul has already told you, but I'm focusing on the documentation side. So, it's important first and foremost that you record and classify failures in a consistent manner. So that's your focus when you're doing these kind of tests. All testing should be relevant and repeatable. I think you've heard that a couple times now. And then I think you need to have an education program. So when you're the technician filling out these forms, to me it's real important that you have a base understanding of SIL ratings and what the end game is when you're collecting this data, so that they understand how important it is to document the failures properly. Utilizing templates, I think, is a great idea. And today there's really no excuse not to have templates with the way you can do things electronically, but you know, you're going to have a different template for a single device. You're going to have a more elaborate template for a full function test, kind of like what Paul did. You know, the rating came up at 350, but then when you did the full function test, it dropped down to 190. And then you'll have a different template for an emergency shutdown, and on and on. I mean, you start out with a template, but you customize it to fit the scenario of what you're trying to test, your proof test. And of course, you need to verify your test plan and get input from all the stakeholders. But I think it's very important to review especially the initial tests that you perform using your plan, and really validate every little detail and make sure there are not blanks that are going to be left, and that everything is relevant, repeatable, and so on. And this is from Paul. You really should use some self-auditing strategies. There's no reason you can't make improvements on what you're doing as things change and evolve, but you can use your own corporate staff. We're seeing more and more reliability engineers out there. I'm sure this is a major part of their job function. And obviously you can utilize consultants depending on your organization. But I highlighted this text. I mean, the goal here is to strive for high quality data. So you want to enable your personnel to give you the very best detail and try to be thorough. So by utilizing a database and handheld devices, you can take some burden off the data collection. And this is more of a training and procedural aspect, but you know, in general, you can say more detail is better. By just saying repaired air leaks, that's great that comment was made in the margin, but really it would be nice to know a little bit more about what was the root cause of the air leak. And then finally, well, not finally, but all failures that occur during testing and the lessons learned should be reviewed. So I think, as Paul pointed out, this is an evolution, you know, doing these kind of tests. Things change. If 30% of your sensors are different than what's in the project drawings, you know, obviously these things need to be fixed for future testing. And finally, my last point here is, you know, having an effective change management in place is critical, and you need to be inflexible so that you're doing things correctly and operating your plant at the safest levels. So this is a little summary of good practices, and as I said, there's a lot of information out there on the web that you can leverage here. And getting involved in some of the organizations Paul is part of with ISA would be a great place to start. So with that, let's see how one way that you could do a test, and it's actually the first example I gave, that minimalist test. Roy's going to show us how to do it electronically. So take it away, Roy.
All right, thanks, Ned. But first, today's live demo is presented to you by bubbly water, because life is better with bubbles. See? And this is the strongest thing that Ned'll let me drink. So let me share my screen here. So one other thing is that I'm in a chair somewhere in the South. I'm not even really sure where I am, but this makes me feel like a therapist almost, and that would mean that you're all here for group therapy. And we're talking about calibration. So I'm here to help, and I'll be your calibration therapist during this live demo. And my motto is, I'm not happy till you're not happy. Actually, I might need some help on that one. But I did ask Ned, why do I have to do the demo thing? Why can't I do the presentation part and he do the demo? And Ned replied, well, if everybody sees you do it, then they know that anybody can do it. So I thought that was nice. Wait, I think I actually resent that. But let me share my screen and see what we're doing here. So Ned, let me know if, am I sharing my screen now?
Yes, looks like you have an app that you need to activate.
Okay, so I've got an app on my phone, and so this is it right here. I've got a phone here, and I could be doing this app on my tablet also, or I could be doing it on a laptop, something like that. But what I'll do is I will push the button. So I've just fired up this B Mobile application, and we want to get paperless here. And the idea is we have so many different maintenance inspection items, and if we don't document it, it didn't happen. I have two items here. One has 34 checkpoints, and the other one has 19. Let me start off by just clicking on the larger one first. This one has a description. This one hasn't been ticked or started yet, but on the checklist, there are pre-check items, and those include verify the drawings, verify interlock diamond, verify interlock is ready for testing, verify operations and PCE are available, etc. And then on to the individual steps. And these are defined by your current process, and maybe you're doing check marks on a piece of paper and you're walking around with a clipboard. So electronically, we can grab all this data and then put it somewhere. So when you do need to provide the documentation, you just pull it up on a screen or print out a piece of paper or save it as a PDF and forward it through email. So let's do this one. Unit 103 online flare. Okay. Flare load reduction, SIS testing procedure. Here's my description. These are all the documents that this refers to. And I have 19 open. If I wanted to, I could go through the checklist and look at each of these individually. I don't want to do that. Let's just kick it off.
Roy, go back to the description and scroll down. Hit that more information.
Yes, sir. So, okay. You know, I was wondering where the work order number was, and here it is. So here's my start date and my end date. All right, device ID. Did I miss anything on this?
You're supposed to do this by Valentine's Day.
Oh, you know what? That reminds me. I got something else to do on Valentine's. No, I just lost it. Okay, so I'm going to hit start. Here's the first one. Complete the requirements of the SIS pre-inspection checklist. I have three options: pass, fail, or skip. So you get to define whatever this is. So let me pass this first, and I'll say I'm done with this. I have it set to automatically go to the next step. So this one is conduct physical inspection. Yeah, okay, yep, that one passed. I am pretty good. I'm going to run through these. Let's say this one, I'm going to skip it, but it's set up that if you're going to skip, you have to put in a note. So I'm skipping it because I said so. Sod said. Okay, I'm not really very good at this, Ned. Okay, so here's my note, and I'm choosing skip. So I skipped that one. This one is passing, and maybe we have one verify control valve FV151 is still in service. Maybe there was actually a problem. Something needed to be righted, or it was a problem, but I fixed it here. So I'm going to put fail. This one failed, but I have to put a note in here, and I'm going to say that I resolve the issue, and I'm going to choose fail. Now this won't invalidate my entire inspection here, but I'm saying that point had a problem, and I want to document it for later. So this one passed, and I'm on number 7 of 19. I'm just going to click through these. Verify solenoid valve cannot be relaxed. Okay, fine. And just for the sake of time, I'm skipping through these. But these are all individual questions that have a pass, fail, or a skip option. And while I'm doing this, Paul or Ned, do you have anything to add while I'm passing all these tests because of my amazing technician ability?
Well, with your training, I would say you need to give better information on that fail and the skip. That you're a little light on your
my notes.
Yes.
Otherwise,
you're doing a good job.
Detailed as you. You give perfect examples every single time, and it always relates to something real. That's a high bar, Ned. I don't know if I can hit that. And So we have complete a non-conformance checklist with any non-conformance items not resolved during this inspection. Okay, done. And finally, the completed procedure shall be sent to instrument reliability engineer for archiving. If the instrument reliability engineer position is vacant, then the manager of power and control will be responsible for archiving the document. Pass. And once this is complete, we have a summary: 17 passed, 1 failed, 1 skipped, none open. And let me put tested by, you know what? I might have Ned's. I could put your name right here, or I could be Peter Parker. But you know, let me put my name in here. So Roy Tomolino, and I'll say I put in a quarter of an hour, 0.25. Really? Is it not going to take a fraction? I did 1 hour. And we have temperature. So what were the environmental conditions? So let's say we were at 73 degrees Fahrenheit. The barometric pressure was 14.6 because we were 200 feet above sea level. And the humidity was 77% because I'm somewhere in the south. Maybe it should be 107. Now, we get to choose overall whether this entire thing passes or fails. So I'm in control of this, and however I've been trained, even if I have a failure on one of the points, it doesn't necessarily negate the entire test that I've done. So I'm going to choose that this entire thing passed. And with that, I'm actually done. I can go back to my main screen. And now, since I have one inspection that's been completed and it's under the passed, I have one that's open that I still have yet to do. If it would have failed, then it would have shown up right there. Now, let me, a little bit before this, I went ahead and just saved this certificate as a PDF. So with the PDF, this is all the information regarding the instrumentation that I've just run an inspection on, and each of the individual items are here. My pre-inspection, this passed. Now I would go through here and modify this so I had some color and it was more obvious on where I had the failure, because down here on 4.0 I had a failed, and I put in testing fail. And let's see if I had any skip on here. So this is my actual paperwork, and this lives in a database, so I do not have to print this out and file it physically unless my procedure tells me to do so. I can put this in the database and simply bring it up and get it electronically or print it out on demand if required. So with that, let's take it over to our second Q&A. What questions do you have for us?
Thank you, Roy and Ned. I appreciate it both. All right, so this is our final Q&A session. If we do not answer any of your questions during this final Q&A, we will follow up with an email and have an expert answer them accordingly. So our first question is, if it's considered acceptable to test the instrument through its range separately, and then for the functional test to utilize the instrument's loop test function to cause the trip for the test?
Paul, you want to start it? I have an opinion, but I'm not sure how it impacts SIS.
Lindsay, read that one again, please.
All right. Is it considered acceptable to test the instruments through its range separately, and then for the functional test to utilize the instrument's loop test function to cause the trip for the test?
Well, I'll take it. So I don't like that because it's you're not checking reality. So instead of just, I mean, why don't you just disconnect the sensor and use a little simulator and simulate 4 to 20 into the system? I mean, I think if you're going to calibrate the instrument and then use that instrument to actuate the other activity, the alarming and things that are supposed to happen, if it's pressure, you should be using a hand pump and exercising that transmitter physically. If it's a temperature, that gets a little trickier. If you can utilize a dry block, that would be great. to simulate the temperature all the way through the loop. But you may have to disconnect the temperature element and simulate that into the transmitter. But you want to get as much as the instrumentation into the test as possible.
To add to that, I agree. The calculations I was showing is how you can model the impact of potentially less than perfect testing. So if you can't test the liquid level float with liquid, the idea of using a test function on the device, that's not a test. Granted, on a large storage vessel, you don't want to raise the level high just to test the sensor and then use thousands of gallons of oil to do that. But your test, again, needs to be thorough. If you want to test for high pressure, like, for example, your set point's 100 PSI, as Ned described, well, you pump the pressure up at 100 PSI and you want to see the thing react. If it doesn't react, then you're doing further checking. Maybe it's out of calibration, but you don't want to calibrate stuff first. Your functional test is your as-found condition. You test it. Does it respond like it's supposed to in the real world? If it doesn't, then you can do further troubleshooting.
Okay, thank you so much for that. Our next question is, safety inspections suggest offline only. What information is available for continuous online process regarding safety monitoring?
There's nothing in any document that says your testing has to be done offline. If you've, again, got a 7-year turnaround, you need to test more often than 7 years. So it's perfectly acceptable and common to build in capabilities for online testing, whether it's bypasses around a sensor or bypass valves around a valve. It just depends what the calculations that I was showing earlier. You can determine what your test interval needs to be. And if you can't do that, or you need to do it more often than every turnaround, then you need to build in online testing capabilities.
Yeah, you have to be kind of clever, but in a good way. It's going to cost you money to do some of these online things, but if you can stretch out that maintenance interval, you know, you're coming out way ahead. But yeah, you're going to have to build in exercises for those valves, because you can't just let them sit there, for sure.
Anything from you, Roy?
Seriously? Does my mic even work now? You probably have me muted.
Okay, I'm gonna say that's a no. Okay,
And
moving on.
if there's any further add-on or clarify any of those questions, feel free to re-ask or clarify if we didn't give you an answer that's satisfactory.
Yep.
Absolutely, great point, Paul. All right, on to our next one. Can you determine failure rates based on vendor data and standard tables when no FIT data is available from the vendor?
Okay, FIT is failures in time. It's one measure of failure rate that one particular organization uses. Many other documents and books and records would just show failure rates and failures per million hours. Failures in time is failures per billion hours. Don't need to get into all that detail. In my book, it covers the various sources of failure rate data and somewhat you could consider the good, the bad, and the ugly. The vendors, you always ask the vendor for failure rate data, but you need to be extremely cautious over some of the numbers they may provide, because if they give you a number, you need to ask them, where did they get the number from? Now, if a solenoid or valve manufacturer got their number by cycling a device 10 million times and never saw it stuck, so they say the dangerous failure rate is incredibly small, I'm not using that number because I don't cycle the device 10 million times. It sits there for a whole year and never gets stroked. The failure rates will be totally different. So I would, if you can't get a realistic number from the vendor, I would turn to some of the third-party data books that are based on industry maintenance records that will give you realistic stuff that typically differs from the vendor by 1 or even 2 orders of magnitude or more. Some vendor numbers are just absolutely outrageous. Exida, which is the group that publishes and only uses FIT, failures in time, they have a very good database online. A lot of final element information is available at no charge on their website, and all of the certificates they have are available free at no charge. So you can actually get failure rates on a lot of devices Now, those failure rates are not based on maintenance records. They're based on a failure mode effects and diagnostic analysis. These are all things we cover in the longer ISA classes. But the best source of information is actually your maintenance records. Now, a lot of people would say, well, we don't have it. Well, the standards say you're supposed to. They said, actually, the OSHA regulations said you should have that stuff back in 1992 based on your maintenance records. So that's what all this testing and the documentation we've been talking about here is for. As last final example, and then I'll shut up. I know a major end user who had no failure rate data on a particular device. They looked in generic data and they were assuming a 50-year mean time to fail. So only 1 out of 50 devices would fail in a year. That's what they based their design on. After years of operating and having records, they found the mean time to failure was actually 5 years, an entire order of magnitude different. This has a dramatic impact on what are you going to do now, because you got something you have to fix. But if you don't have the maintenance records, you wouldn't even know there's a problem. And if you didn't know there's a problem, you could have an accident and not know why. And the audit would then check information and say, well, I'm sorry, you're guilty. You made this outrageous assumption in your design. You had the records that you never looked at that would have shown you had a problem. So we're trying to prevent accidents is why we're doing all this. So you don't want to be the next Bhopal. You don't want to be the next Texas City or Deepwater Horizon. And if you think, well, geez, we've never had an accident here, we are safe. No, it just potentially means you're very lucky. Remember, they said that one day before Bhopal and Chernobyl and everywhere else. So I'm not trying to scare anybody. I'm just saying regulations say you have to be doing this. They have to follow standards, and the standards talk about this level of detail and why you're doing the testing and why you're doing all the maintenance recording, so you can track information to see if it matches your original assumptions and design.
Yeah, I would add, this is really critical stuff. You want to be conservative, but at the same time, you want to be right. You don't want to be over conservative, but you certainly don't want to be light in your guessing and estimates. So yeah, you need to make sure you're right in these calculations.
Okay, I guess for our last question for this segment, what level of coverage is needed for partial stroke test versus full stroke testing?
Okay, there is no recommended level of coverage. You do the calculations as I was showing to determine what the coverage needs to be in order to meet your integrity level target with the hardware you have, based on whatever your partial stroke test frequency is. Are you doing it weekly or are you doing it every quarter? That has a dramatic impact. There is a technical report from the ISA 96 Committee on Valves that is an entire technical report on partial stroking and the different methods of doing partial stroking and the different levels of automatic diagnostic coverage you'll get. Some of the very simple methods, you may only get like about a 30% diagnostic coverage factor. Some of the much more detailed and automatic and more frequent methods, you can get it up to about 80%. So it's going to be in that range. There is no target, just as there's no recommended SIL, safety integrity level, for whatever your function is. You have to determine what the performance target is, and then you do the modeling to see, will my hardware meet it, or do I need to change my design? Maybe you need redundant valves, maybe you need more frequent manual testing, maybe you need more frequent partial stroke testing.
Yeah, that's one thing I've learned with this session, is that you kind of have to back into these intervals. There's no magic formula out there, and so when you determine your SIL, that's going to be your lead determinant on an interval, and then you need to see if you're not doing it enough. You got to figure out ways to do it more often. So it just
yeah, to add what Ned is describing. So if you say, for example, SIL2 is your target, and and I've had this lots of times when I'm brought in to do the verification calculations. They design stuff with non-redundant sensors and final elements. They're assuming yearly testing, and all I do in my modeling is show, sorry, you don't meet your SIL2 target. Well, you need to change something now, and you need to do this analysis early in the design before you start purchasing and building stuff. Maybe a switch isn't good enough. You need a transmitter. Maybe a standard transmitter isn't good enough. You need a safety certified transmitter that has a much higher level of diagnostics. Maybe you need to do partial stroke testing. Maybe you need fault tolerant devices. Maybe you need to change your design. That's what the whole point of doing the calculations early in the design phase. That's what it's for, so you can save money and get it right in the first place.
Very good.
All right, thank you, gentlemen. Time's up. I really appreciate everybody's contribution. This session is over, but remember, we will be emailing all the other questions that we didn't quite answer. From now, we are going to pass it on to Katie Turner.
Thanks, Lindsay, and thanks, guys, for a very informative presentation. One more quick promo before we go. There is a Beamex blog out there that includes articles about calibration and also related to the topic here today. And one in particular is called Proof Testing Calibration by a Different Name. So I encourage you to check that out. If you subscribe to the blog, you'll get notifications about when new articles are posted. All right, and once again, we want to thank you, our audience, for joining us today, for your time and participation. There was a lot of good questions, and I know several that we couldn't get to. So we will follow up in an email to answer your questions, the presenters or the experts will. And I also will be emailing you a copy of the recording along with the resources that I've promoted here today. And if you'd like to reach out to one of our presenters directly, their contact information is on the screen as well. And last thing, there will be a survey that will appear in your browser at the end of the webinar. Please fill that out and let us know what you want to see next. And we hope that you will join us for our next webinar. And we hope you learned something here today. Thank you, everybody. Bye-bye.